Okay, that all looks appropriate. Okay, checking over our attendance. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everyone but Eliezer. Okay, we are going to talk about the death stage. I have 40-odd slides here. I clearly don't expect to go through all of them, in case anyone thinks I'm going to go through 43 slides.
I believe you're at 10 crossing.
What was that?
That's depressing.
Yes, it is depressing, but we want to learn about it. So, up here is the abbreviation for the sun's lifetime. So the sun has its beginning stages of being a protostar for about 20 million years. Then it has its main sequence life where it's fusing hydrogen to helium for about 10 billion years. Notice M versus B. Then it goes through its death stages, and you notice that fusing hydrogen in a shell lasts for about 1 billion years. Fusing helium in the core, only 100 million years. That's 1/10 as long. Right, this is 1/10 of the predecessor. That's 1/10 of its predecessor. That's 1/10 of its predecessor, down to 10 million years. And then we go to 10,000 years. That's 1/1000th of its predecessor. So you can see the stages are going faster and faster as the sun is going through its death stages. Now, I say you can see. These come from, what's our evidence for this? 2 things. One of them is our computer modeling based on the physics we understand here on Earth. And so we have a hypothesis, theory, but you don't want to stop there. What do you go with that once you have the predictions of your model?
You test it.
You test it. And so in this case, the testing is looking out there, and specifically this is going to be looking in clusters where you have all the stars of the same age, and you look at what are stars that are the size of our sun doing at different ages to test it. I'm not going to go through all the words on that. We've gone through them. This picture is illustrated on an HR diagram, the same thing. So you have this birthing part, the protostar. Remember, what was the time for the protostar? $20 million years on the protostar. They started at time 0, the main sequence. And notice it goes out to 10 billion on the main sequence. The textbook says the calculations say 12 billion. We usually just round that to 10 billion. So 10 billion on the main sequence. And then we have this red giant branch. What's occurring during the red giant branch?
Expanding its core.
Why? That's correct. Why? The core has run out of fuel, and because the core has run out of fuel, it's crushing in on the core. Now we have a shell of hydrogen fusion going out beyond that, but it's actually the crushing in on the core that creates extremely high temperatures of the core, which creates an extremely high pressure that then pushes out.
How high are the temperatures?
Well, the temperature continues to rise until you get hot enough to fuse the helium. So the temperature will continue to rise until you get to, what was the helium fusion temperature? Something like, well, I have it on the later slide here. I can't remember. The number that's coming to my mind is too high. I'm thinking 200 million, but I think that's too high.
I think it was a 2, wasn't it?
Yeah, so maybe it was 200 million. Anyway, I have it on a later slide, so when we get there, we'll refresh. And so that's what's going on there. Once you have helium fusion occurring in the core, our sun will have a helium flash. Why do we believe our sun will have a helium flash? because its mass is between 1/2 a solar mass and 2 solar masses. Excellent. Thank you for letting me know. Okay, so we believe our sun will have this helium flash because it's between 0.5, which is the minimum mass for helium fusion to occur. If it's less than that, you reach degeneracy and you don't have enough additional collapse beyond that point to cause temperatures to reach fusion of helium temperature. If it's more than 2 solar masses, it never reaches degeneracy. This is electron degeneracy, and immediately just goes into a nice smooth fusion when it gets hot enough. Then we have the yellow giant stage, which is when it's having helium fusion in the core, so the core has stabilized again. Then runs out of helium in the core. Core starts collapsing again, and you will go through the Mira variable. And then notice here. Here is where it starts as planetary nebula. Here's where it ends. The time there, compared to all the other times, is virtually nothing. Right? It was 10,000 years for the planetary nebula stage. And then when the planetary nebula stage is, so we're at 11.11001 billion, plus or minus a couple billion. The reason they keep all those digits is for comparative purposes. Then it's a white dwarf, and it starts as a hot white dwarf. Why a hot white dwarf? Because it was a hot star. But over time, it's going to radiate away energy. Because it's radiating away energy, it's going to have less remaining. Temperature is a measurement telling us how much energy it has. So as it's radiating away energy, its temperature is dropping. And so this line here is essentially a constant mass line with the temperature dropping. Because the temperature drops, it's giving off less radiation. The radiation is proportional to area times temperature to the 4th power. So the area is staying the same, but the temperature is dropping, so it's giving off less radiation. And eventually, this doesn't show low enough, eventually it would get, down here, and it wouldn't be giving off any visible light. At that point, we just call it a black dwarf. So black dwarfs are white dwarfs that have cooled to the point that they're not giving off any visible radiation. The time it would take for a white dwarf to cool off to become a black dwarf is longer than the believed age of the universe. So theoretically, black dwarfs will exist in the future, but could not theoretically exist now. So if somebody were to find a black dwarf, they would say, ooh, time to reevaluate, right? Because that's what you do with the scientific method. If you find something that disproves your hypothesis, you go back and change it to incorporate the new information. But nobody has found one. Now keep in mind, finding a black dwarf would be very, very difficult because it's not giving off light.
So what would be some of the ways that we could find it?
Well, here, something we're not going to get to that I realized just today. This is the last week of the semester. I would love to have 2 more weeks of the semester. I could cover everything I wanted. But one of the things we're not going to get to is talking about dark matter. Dark matter is, we can make measurements that says there's this much mass. How do we make those measurements? By looking at rotation curves. Just like we can find the mass of a star by looking at the rate at which something is rotating around us, or around that star, or the mass of a galaxy by looking at the rate at which things are orbiting it, we find, actually it starts with galaxies. Looking at galaxies, even our own galaxy, if you look at the farthest out stars in our galaxy, their orbits are way too fast for the amount of mass that we can find in the Milky Way galaxy. And so the conclusion is there must be matter that we don't see. And so we call that dark matter. Dark because we don't see it. So for the hypotheses, and at this point they are just hypotheses. They're not even good enough to be called theories, I don't think. One of the hypotheses is what they call WIMPs, which is weakly interacting massive particles. So weakly interacting means that generally nothing interacts with them, hence you don't see them or detect them. Neutrinos would be an example of a weakly interacting particle. But neutrinos have a very tiny mass. So this is massive particles instead of neutrinos, but weakly interacting. So that's one hypothesis about what that dark matter might be. Another one is machos. Get it? Machos and wimps? Yeah, because scientists are funny, funny people. So machos is massive. That's what the MA is. What is the C? Massive something halo objects. I think it's massive cold halo objects. Well, the halo is the part of the galaxy that's above and below the disk. Galaxies, well, a spiral galaxy is shaped like a frisbee. And the halo is up and above and below that frisbee. And so, essentially, these machos would be things like, perhaps, black dwarfs. Massive objects out there in the halo that we aren't detecting. So there's an answer for dark matter that essentially invokes these things that have not been detected. Yeah?
If they did discover a black dwarf, would they have to reevaluate the age of the universe, or just how long it takes for it to start to cool?
Well, you actually have to look at every option. You can't simply say, well, this is sacred, this is not. So you'd have to evaluate where it could be. I mean, to be scientifically honest, you'd have to evaluate every option. All right, moving forward. The red giant expansion. The red giant expansion has an interesting aspect to it that I decided to leave this slide in. The outer layer cools enough that you actually form these things that the textbook calls carbon flakes. That is, you form little organic molecules, kind of. Right? Organic because they're carbon-based. And those things then are pushed outward by the radiation pressure. They're going to catch more than a single molecule would as far as being like a sail. And so they're pushed out further. Those also play into the variables, the same carbon flakes. And so that's part of the reason why you have the giant stage. And those particles that are getting pushed out continue going. And that's why you have the massive outgassing, the massive amounts of mass that are being blown away during the death stages. So it creates a very high-speed stellar wind. And then those particles that were blown off, when the star eventually dies, when its core is no more, you'll have a bunch of radiation that goes barreling out away from the remnants of the star, and when that radiation goes through the gas that's been already emitted, it will absorb radiation, give off radiation, and give us pretty lights. So this is, it's called the Hourglass Nebula because it kind of looks like an hourglass, but this here is all part of the planetary nebula. Everything you see in here that's giving off light is either the original star. We can find the core of the original star. That there inside of my box is the white dwarf.
Whoa.
And then zooming back out, all of the rest of this is gas that used to be part of that white dwarf that was blown off during its during its giant stage. And now radiation from the remnant has gone out and caused it to light up. So you can see that's clearly a non-uniform distribution of the mass. The mass didn't just go off as one big spherical shell. And so planetary nebulae, it used to be thought they must be uniform and it's funny based on the way we're looking. But of course, these things are rotating, so it does make sense for there to be more of a cylindrical symmetry for the material blown off than a spherical symmetry. Here's another picture. Can you see the white dwarf there?
In the center?
Yep, there's the white dwarf there. This is all gas that was blown off that's now being lit up, giving us our planetary nebula. Now, this could be in structure just like the Hourglass Nebula. Just view it at a different angle. Here you're seeing a sideways aspect, and here you're looking just straight down the end of the hourglass. It could be like that, right? Take a lot of study to determine if that's the case. How would you study it? Look at Doppler shifts. The Doppler shifts will tell you that if it's coming toward you or going away from you. And so you can get an idea of exactly what's going on when you look at this to better understand what it is. The white dwarf itself initially has a surface temperature of about 25,000 kelvins. Now let's compare that. What's the surface temperature of the Earth's sun right now? Yeah.
5,000.
Okay, 5,800 kelvins. Rounded off to the nearest 100 or so. So 5,800 kelvins, this is about 4 times that temperature. Now, of course, the core of the sun is at 15 million kelvins. So it's much cooler than the core, much hotter than the exterior. What is this white dwarf going to be? What's the atom we're left with when the sun is all done? When the sun is all done, when it's done all the fusion it can. Not iron. Sun isn't massive enough to do that. Sorry, I changed it to a new one. Well, Caleb helped me. Carbon. The sun is going to end fusing helium into carbon. So this is going to be primarily carbon and electrons. And it's the electron degeneracy that holds up the white dwarf. The electrons are degenerate, just like when we have the helium flash degeneracy. The electrons can only be pressed so close, and that's keeping it from being compacted anymore to set its size. Now, really interesting things about this. If you put more mass on a white dwarf, it will compact a very small amount. So the more mass it gets, the smaller it gets. Bigger white dwarfs are lighter white dwarfs. Smaller white dwarfs are heavier white dwarfs. White dwarfs. And if you get up to 1.4 solar masses for the total mass of this white dwarf, the Chandrasekhar, is that right? I've been working on it. Shaker?
Yeah.
Shaker. Chandrasekhar limit, then the electron degeneracy is crushed. It's enough force to overcome the electron degeneracy. And when that happens, which is not on this slide, then it blows up. Before we talk about it blowing up, we're going to talk about eruptions on the surface of a white dwarf. I say eruptions on the surface of a white dwarf, and it sounds ridiculous. We think of the white dwarf as just this ball of carbon, or maybe a ball of helium if it was lower mass and never fused helium into carbon. So how can I have an eruption on the surface? That can occur if and only if it's part of a binary system. If it has another star, companion star, and that star is dying. If the companion star is dying, going through a giant stage, it's going to be blowing off a lot of mass. So mass that used to be part of the companion is now up for grabs. Now, doing calculations, we can calculate a volume that belongs to one star and a volume that belongs to another star. Anything within one volume belongs to star A. Anything within the other volume belongs to star B. But if star B is dying and blowing material out, it will blow material that it owns over into the other star's area. And so we call the shape of the material it owns the Roche lobe. Roche is spelled like this. I always said Roche. It seemed right, but it's Roche. Yes, exactly. It's the same Roche. And so we have a point here where the two Roche lobes meet. And if mass from the dying star gets to that point, it just transfers across and is pulled in by the white dwarf. So the white dwarf can gain mass if it has a dying companion. And as it gains mass, high temperature on the surface, you gain mass, it comes and compresses and gets hotter and hotter. And when it gets up to a high enough temperature to fuse hydrogen to helium, what temperature is that? 15. 15 million. Hey, you took a shot, right? When it gets up to about 15 million kelvins, then you're going to start fusing hydrogen to helium, and you have suddenly an eruption on the surface of the white dwarf of fusion of hydrogen to helium. Now, what do you suppose this does to the white dwarf? The answer is nothing. The white dwarf is already really compressed. The gravity is super strong. So it is not going to be very affected by this explosion on the outside. What happens is you just create a little more helium that then coats the surface, and your white dwarf got a little bit bigger. And so a white dwarf can go through multiple stages of this. Each one is called a nova, nova being Latin for new. Called a nova because if you look at the sky, all of a sudden, it's bright where it was dim before, and then it fades again. And so it's generally pretty reproducible in the timing because you have mass blowing off of one star at a constant rate, being accumulated, gets to a certain level, until you reach that Chandrasekhar limit. Shaker. I'm practicing, man. by tiny amounts. Okay, so here are pictures to illustrate what I just tried to explain. So here is trying to illustrate what's happening when it has the explosion. Light goes out. Here's a photograph, because the photograph is a little more telling. You see, here's the remnant, the white dwarf that's actually here. So this would be early in the explosion. This would be later in the explosion of the surface just... And it just gains a little mass. Okay, so this slide should have the word Chandrasekhar. Shaker. That's what I've always said, but I learned on Friday that that was wrong. It's better to be right. So, if the mass exceeds 1.4 solar masses, then the white dwarf can no longer stand up. It will be crushed by its own mass. And so when this occurs, when it gets crushed by its own mass, then it actually just gets decimated. It blows up, the entire thing erupts, and you're left with nothing but a cloud of gas. What do we call a cloud of gas? Yeah, it's a nebula. I was pointing to... Yeah, to Eliezer, because he said earlier, not today, but earlier lecture. So the type 1a supernova is the white dwarf that has exceeded the Chandrasekhar limit. Man, it's bad. Even Megan's like, yeah, you're learning. It's exceeded the Chandrasekhar limit and has collapsed, had a big explosion, and leaves you no remnant at all. Type 1a supernovae are very reproducible. Why very reproducible? They always have the same mass, and they have pretty much the same chemical composition. Same mass, same chemical composition, it should collapse the same. So here is a light curve showing us what the luminosity is like for a nova, or excuse me, a type 1a supernova. First thing to note is this is the luminosity in solar mass, or solar luminosities. How does this compare to the light given off by the sun right now?
Way brighter.
Almost 10 billion times brighter than the sun. So these novae, you might have a white dwarf that's very, very faint. But if it undergoes a supernova, it's extremely brilliant. So these are not hard to spot. They're fairly easy to spot. They grow in brightness very quickly. You see there, it grows in a matter of, let's say, 10 days to maximum brightness. And then over the course of the year, it fades away. So they are very distinctive. If you find a type 1a supernova, how do you identify it's a type 1a? You look at the spectra of the light. If you find a type 1a supernova, you know how bright it was. If you know how bright it was and you measure how bright it appears from Earth, then you can determine its distance away. So these are really good for determining the distance away to very far places. Okay, clicker question numero uno. What end stages, so enter all the correct answers and then press enter, will our sun experience?
Enter all of them?
All of the ones that are correct.
Is there more than one?
There's more than one that's correct.
Final what? Oh, okay. How many? Like, as many as we can first?
As many as you believe are correct. Okay, everybody's answered. Did it allow you to put in more than two? Okay.
I only put 3.
Put 6.
Okay. When you look at this, there's one that everybody agreed on. It's going to become a white dwarf. That is true. It's good.
So you will get the red giant. That's the next one.
It will, the first thing it's going to hit of all of these is what Alina said. It's going to become a red giant first. So red giant is correct. So these two here are definitely correct. This one here is probable. The planetary nebula. It probably will form a planetary nebula. The question on that is if it will have enough energy in the final collapse to go out and excite all of the mass that's been blown off. Now, we'll be in heaven to observe this, and we'll be able to tell at that point. Of course, by the time we're in heaven, we'll be able to figure it out without having to wait to see it happen, right?
It's going to be a great movie.
And if you're not in heaven, we'll think of it. Yeah. Okay, we had two people that said a type 1a supernova. What has type 1a supernovas? Always white dwarfs, right? So why won't our sun become a type 1a supernova? It will not. It's not now, but it has to start as less than 1.4 solar masses and get up there. How does it gain mass? Yes, white dwarfs that are part of a binary. So that when the binary companion starts dying, it can start gaining mass and eventually maybe have the type 1a supernova. So our sun cannot do that. And of course, novas, what has a nova? The same thing. The novas are the steps as it gains mass, and then this type 1a supernova is when it's reached this ultimate mass, and the Chandra shaker limit, and collapsed. All right, now let's go to the death of massive stars. So we've gone from a 1 solar mass star to a 25 solar mass star to look at how it dies. And you notice that this looks very different. It's pretty much just a horizontal line. It's getting cooler and staying just about the same brightness. Well, getting cooler and staying just about the same brightness means that it must be growing in size. So it's becoming a giant. So you have a red supergiant phase here, a yellow supergiant phase here because it was hotter, a blue supergiant phase here because it was super hot. And so it's going through these, and the times once again are shown. It has approximately 6.5 years on the main sequence, 6.5 years, 6.5 million years. And then 7 million years is a blue giant, and then it goes very quickly, or actually, it's not, this is 1/2 a million years, so 500,000 years. You got to take the difference in them. So 500,000 years as a hydrogen shell fusion, and then it doesn't even give us the time for the helium core, and it gets to its death point another 700,000 years after it was the yellow. Core collapse, how does that compare to the total lifetime of our sun? Total lifetime was 11.11001 billion years is what it said on that previous graphic. So how does this compare?
I guess burn out quick.
Yeah, it's less than 1,000th as long. Its lifetime is much shorter because it's 25 times greater mass. Notice for the very large, it will fuse carbon, neon, oxygen, then silicon. So let's look at that a little more carefully. Our star will fuse hydrogen to helium, then helium into carbon through that triple alpha process. Well, a more massive star will get hot enough in the core to fuse carbon, and we'll see actually 2 forms of the carbon fusion, and then go through additional steps, and you will have multiple shells of fusion. You'll have on the outside a hydrogen shell that's fusing hydrogen to helium. And inside of that, you'll have fusion of helium into carbon. And inside of that, you'll have the fusion of carbon into neon. And so you just have them all nested. You have one form, starts growing out, core collapses, start fusing something in the core. That stops. Another shell forms, starts going out, core collapses, start a new fusion. So it just keeps repeating that process, getting hotter and hotter in the core. And each time it gets to the minimum temperature for a new fusion, that one begins. So all at one time you have all of these shells, which is pretty amazing. And here is a breakdown for a 25 solar mass star of the times for each thing. So 7 million years fusing hydrogen to helium. And then 700,000 years fusing helium into carbon. 300 years fusing carbon into neon. You notice that change from 700,000 years to 300 years. Much hotter and many fewer atoms. Because to form the carbon, you had to combine 3 heliums, which was 4 hydrogens. So you cut it in 1/4 as terms of number of atoms, then you cut that number 1/3, so you're at 1/12. And so your fuel is 1/12, and then you take 2 of those, you fuse them at a super high temperature. So here we have the temperatures. It was 100 million, not 200 million, to fuse helium into carbon. 200 million to fuse the carbon into, with the hydrogen to oxygen. 600 million to fuse carbon into neon. And then neon fusion, 1.5 billion kelvins. Oxygen fusion, 2 billion kelvins. And then finally, the silicon fusion, 2.5 billion kelvins. And notice the time for that last silicon fusion to occur. 1 day. All of the silicon left of the star fuses in 1 day. And at that point, it's all she wrote. Why is it all she wrote? We've talked about it. I don't think that the new graphic back there has the diagram. Here's the diagram, though. This is the diagram that shows the binding energy per nucleon. That is basically telling you how tightly a nucleus is held together. And fusion will occur going from smaller elements toward the most tightly bound nucleus. So fusion will occur from things less than iron up to iron. Fission will occur for things larger than iron going down toward iron. Why does it not continue on past iron? Because instead of producing energy, it would absorb energy. So if you started fusing, let's say, iron, you would start quenching the temperature. You start cooling it down. And so because it takes such high temperatures to start fusion, if you start fusing iron, your temperature will go too low to fuse iron anymore and it'll just stop. So that's why it ends there. So more massive stars, stars that are massive enough to fuse carbon, will fuse all the way up to end up with the iron core. Yes, sir?
So could you fuse elements that are higher than iron, or would they, once heated up, would they just split into iron?
This is a good question, exactly where I was going.
Nice.
We have on our world lots of atoms. Of those atoms, the most common atoms are, well, the most common atoms in the crust of the Earth are silicon, oxygen, and iron. And those were because of melting temperatures. All of those are from iron and down. None of those are above iron. But we know that we have elements above iron. For instance, lead, uranium, gold, silver. All of those are larger than iron. Now, the question is, where are all these atoms coming from? According to the research done by astronomers, by physicists, in the 1940s and on, they started studying, okay, so if there was a Big Bang, then you would have had, and that's what the graphic in the back is now, is about the history of the universe. There's a Big Bang, it would have started super, super hot. Super, super hot, so that you didn't have anything but essentially light. But the light would go very short distances, be absorbed, re-emitted. But as expansion occurs, it would cool down, and you could have that energy convert into actual matter, and pretty soon you'd have a whole bunch of protons. And those collisions with protons would form deuterium, just like we saw in our proton-proton chain sequence, helium-3, helium-4, but there is no stable isotope with 5 things in the nucleus. So 4 is pretty much a stopper. Virtually no elements above helium should have been created in the Big Bang according to the scientific theories. Now, you could have a very rare event where you have like a helium and a deuterium come together to form something with 6. So you can get past there, but there's also no stable elements with 8 things in the nucleus. So that's another stopper. By the time you get to the second stopper, no. So according to the theory on how the Big Bang progressed, there should be nothing bigger than, let's see, count them up, nothing bigger than nitrogen, no, not nitrogen, it's way down below that, I think beryllium, in the universe. Anything bigger than beryllium has to have formed somewhere else. Well, we have seen here that during the death of a massive star, we could form everything up to iron, but virtually nothing above iron. So we can account for the common elements of the Earth's crust, but not for the rare ones. Well, the rare ones would have to occur during the very final stage of the death of a massive star. During the very final stage, this core has now just become iron. No more fusion in the core. Every step along the way, what happened when we stopped fusion in the core?
Star died.
Okay? The star died, and the process was it started collapsing in on the core because there was nothing pushing out anymore. And so when you have a star that is in its death stages, has a core that's iron, iron will quench the fusion if you try to fuse it. It collapses rapidly, and you have just massive nucleosynthesis producing all kinds of things that are higher than iron, at the same time absorbing all that energy to quench the process. So everything that's larger than iron is only produced during the final type 2 supernova when the star is collapsing. What you have is the core will be so compressed that you'll overcome the electron degeneracy and force electrons into protons. When you force the electrons into the protons, they basically destroy each other and create neutrons and neutrinos and light. And so you end up with a whole bunch of neutrons and a whole bunch of light, and the material comes in, bounces off of those neutrinos, and reflects outward. You have big collisions, and that's where all the nucleosynthesis is going on. That's where all the fusions are going on, making things larger than iron. And so supernova is the answer, right? That's the short answer, supernova. Anything larger than iron could only be created in a supernova. So if we look at something and we have gold, that's stardust that was created in a supernova, according to scientific theory. We have something that's iron, that's also stardust, but it could have been created in something that was less than a supernova. And so that's what all the words on this are dealing with. We're leading right to where I was going. Good job. Here are some light curves of type 2 supernovae. Notice these are not all the same. There's quite a bit of variation. Why variation? Because a type 2 supernova could be lots of different masses, could be lots of different chemical compositions. And so you have different ultimate brightnesses, you have different durations, you have different spectral lines. These tend to have hydrogen lines in them because stars have hydrogen. Whereas the type 1a supernova doesn't have hydrogen lines because it had fused the hydrogen into helium. Helium into carbon, perhaps. Now, just a technical note, there are other kinds. Here's the words to go with that. Gold, uranium, and all other heavies originate in supernova explosions. Where was I going? Yeah, this one right here. There are other types of supernovae besides type 1a and type 2. The type 1s don't have hydrogen emission lines. Type 1b and type 1c are actually the collapse of a core, like a type 2 supernova, but they don't have hydrogen emission lines. For a class of our level, we simply won't worry about the type 1b and type 1c, right? It won't show up on your test. Okay, so the end result of the type 2 supernova, neutron star. What holds up a neutron star? I think this was a Flip Friday question. It's degeneracy again. But instead of being electron degeneracy, it's neutron degeneracy. So it's once again a quantum physics effect that says you can't compress these things any tighter. And so neutron degeneracy is what keeps a neutron star from collapsing. And of course, there's a maximum mass for a neutron star as well. If it's over around 3 solar masses, you'll crush that neutron degeneracy. And there is nothing that we know of that would stop the collapse at that point. So as far as we know, if you crush the neutron degeneracy, it will be crushed forever. Now, crushed forever means it'd be crushed to a single point, what we call in mathematics a singularity. There are some scientists who say, well, that can't be what really happens. There must be some other force that we don't know about that keeps it from having zero volume. Because what sense does it make to have something that's the mass of 4 or 5 of our suns all compressed to have no volume whatsoever? Other scientists say, I can see it happen. So there's not agreement on what would happen if you crushed that at the center.
So, how could you crush that? I'm sorry?
How could what?
I missed that. How could you crush?
Gravity. Gravity. Remember, we started off the very beginning of the semester, and I talked about the forces. I said gravity is the ultimate winner, in my opinion. Ultimately, when all is said and done, gravity is the one that remains. And so gravity, when you have exhausted all of your fuels, gravity crushes. And if you have enough mass, gravity will crush anything. And so it's the gravity that's crushing it, making it shrink to nothing.
Right, so what I'm trying to figure out is, like with the neutron stars or the white dwarfs, what happens with, that they have that limit where they can't be compressed anymore.
Right.
Is that only up to a certain point, or?
Right. If you get a high enough force, you can actually break it.
Okay.
Right. There's ultimate strength involved. So you can't crush it until you get to high enough strength to break it.
And so, would that just have? Would that have to? Would you have to add more stuff to it and compress it some more, or how would you?
Well, you add more stuff, and that compresses it. Okay, now, a terminology that to me is fairly fresh and new, that means it's, 3 or 4 years to me, is the term hypernova. When I first started teaching astronomy, a supernova was a supernova. A supernova produced either a black hole or a neutron star. But there were these things that were observed, gamma ray bursters, things that were very, very short in duration that had a lot of gamma rays, which are very high frequency, very short wavelength emissions. And there was a lot of controversy about what's causing this. And now they've reached kind of consensus that these gamma ray bursts are caused by the collapse of extremely massive stars. Now, on your Flip Friday, I went with my standard, a hypernova is still a supernova. But the term hypernova is for the collapse of a supermassive star that doesn't stop at a neutron star. It crushes all the way through to create a black hole. That is, you just had so much mass that the neutron degeneracy couldn't stop the collapse. And so the hypernova, very short duration, very high energy emission. And you create, the dashed lines are there to indicate that inside of that is something we can't see. The black hole. So let's end our lecture by, let's end right here. This is starting to talk about pulsars. And that brings up a whole new, the little green men discovery. Because that's what Jocelyn Bell called this. She called this signal the LGM signal for little green men. Quite literally, she was joking, but she called it little green men signal. Okay. I forgot to stop that.
So tomorrow, I know we don't have to go to the lab.
What was that?
Tomorrow we don't have to go to the lab.
No. Tomorrow will be the lab final. So if you still have a lab to make up, or if you haven't done the lab final, then you need to come tomorrow. If you have already completed the lab final and you don't have a lab to make up, then, you're done as far as lab goes. Excuse me? Friday.
How late are you going to be in your office for me to turn in for Friday? So.